The next series that we'll look at is a direct consequence of the integral test, and sometimes can look a little bit similar to the geometric series, but it's a different series, and it's called the P series. And it's the series of n equals 1 to infinity of 1 over the variable n to some constant value p. So when we evaluate that, it's 1 over 1 to the whatever value p is, 1 over 2 to the whatever p is, and so forth, and we add those together. And that's called a P series, and it's a very simple test. It converges if p is greater than 1, and it diverges if p is less than or equal to 1. So in order to see that, like I said, we can just use the integral test here. Because this is a series or a sequence that's very straightforward to integrate. So we would do the integral from 1 to infinity of 1 over n to the p dn, and change that, of course, into an infinite limit. So integral from 1 to t of, I'm going to go ahead and change this into n to the negative p dn. We can apply the power rule to integrate. So this is the limit as t goes to infinity, and if I add 1 to my exponent, I would have n to the negative p plus 1 over negative p plus 1 is the same thing as 1 minus p. I'm going to just change it and turn it around that way. Evaluated between 1 and t. So then the constant 1 over 1 minus p can come out front. And we have the limit as t goes to infinity of, now this is n to the 1 minus p evaluated between 1 and t. And the variable of integration here is n, so I would plug in for that. And that leaves me the limit, t goes to infinity, of t to the 1 minus p minus, if I plug in 1 to any power is just going to be 1, so it would really just be a constant 1 here. So now we just have to decide on what kinds of values for this exponent, 1 minus p, would ultimately make this limit converge, and what would make it diverge. Now, for the integral test to be satisfied, what needs to happen is this result needs to be a real number. In order for that to be a real number, I think what we need to happen is for this term right here to go to 0. If that goes to 0, so what we want to happen here is we want the limit as t goes to infinity of t to the 1 minus p to be equal to 0. So the way that we would make that happen, let's rewrite this as the limit as t goes to infinity of 1 over t to the p minus 1. All right, all I've done is negated this exponent. So when you negate an exponent, you can bring it down into the denominator. So I basically did that. I negated it, brought it into the denominator. But the act of negating and bringing it into the denominator cancels out, so this is still equal to each other. So I want this limit here to be 0. So in order for these terms to go to 0, what needs to happen is this exponent needs to be a positive number. So I need something like, 1 over t squared. That would result in 0. Or 1 over t to the 1/2. That would still result in 0 when we let t go to infinity. But if it was a negative number, if it was like 1 over t to the negative second, that would be the limit as t goes to infinity of t squared instead, which would run off to infinity and not go to 0. So what we need is for the exponent p minus 1 to be positive, so greater than 0, which means that if p is greater than 1, then what's going to happen is this term will go to 0, and therefore this limit will exist. So provided p is greater than 1, whoops, the next thing that would happen is we would get 1 over 1 minus p times the limit as t goes to infinity. This term would go to 0, and when it goes to 0, we end up with, say, negative 1 over 1 minus p. Or I could probably simplify that to 1 over p minus 1, but that's okay. It's a real number, and that's great. That tells me that the integral test passes. If this had gone to infinity, the whole thing goes to infinity, and then that's going to happen when p is less than 1, the limit diverges. So then the last question is, what would happen when p is equal to 1? So if p is equal to 1, I would have this limit as t goes to infinity of 1 over t to the 1 minus 1, which is 0. So effectively, this would be 1 over 1, because t to the 0 is 1, so the limit would be 1. It would exist. So it looks like everything would be fine, except when p equals 1, we go back to this right here. If p equals 1, oops, not 0, but 1, we would have 1 over 1 minus 1 times the limit as t goes to infinity of t to the 0 minus 1. So this would result in 0. This would result in 0, which would give me division by 0. So it's going to not exist there. So we can also say that if p is equal to 1, the limit's going to diverge as well. So that should give you an idea then what happens with the p series. Now, the application of this is pretty straightforward. So for instance, this next example, determine whether the following series converges or diverges. Well, if we can apply a p-series test, then that's great because it's a very easy test to apply. All right, so this could be rewritten as a series as n equals 1 to infinity of 1 over n to the 1/3 power. So that means p is equal to 1/3, which is less than 1. All right, don't worry about the less than or equal. You can include that if you like, but it's, less than 1, greater than 1. We know that equals 1 is diverging. But less than 1, that diverges. So therefore, this series diverges by the p-series test. So it's a very easy test to apply when it does apply. Do be careful, because even if this was slightly different, like if this was 1 over the cube root of n plus 1, it's no longer a p-series because of that plus 1. So it's only very specific situations where this applies. What's nice about the p-series test is it's easy to make a series that you know converges or diverges, and you can generally use that and compare that to some other similar series, and that's kind of what we'll look at later on in the chapter. But these next examples, let's walk through them. Here, I think I can write this as a p-series, all right, where n times the square root of n would be n to the first times n to the 1/2, which would be n to the 3/2. So p is equal to 3/2, which is greater than 1. So this converges by the p-series test. Next up, determine whether this series converges or diverges. So, of course, if there's just a constant multiplier, you can always pull that out. And then we can rewrite this as n to the 1/6 power. So that says this is a p-series where p is equal to 1/6, which is less than 1. So this diverges. Okay, one last one. Determine whether this series converges or diverges. Well, if both of these happen to converge, then we're actually able to split them up into two separate series. So I could actually do even better. I'll say 4 times the series of 1 over n times the cube root of n would be n to the first times n to the 1/3. And you would combine these by adding the exponents, so that would be n to the 4/3 power, needing a common denominator there. All right, then plus the series n equals 1 to infinity of 1 over n cubed. All right, so the first is a p-series. With p equal to 4/3, and that's bigger than 1, so it converges. And this one is also a p-series with p equal to 3, which is bigger than 1, so it also converges. And that's great, because the thing is, you can only split up a sum like this if the individual sums converge themselves. So if one of these ended up diverging, then that wouldn't have actually given us a result. So we would have to go back and maybe algebraically combine the series and then retry from there. But since these both converge, we can conclude that the overall sum also converges. And that's all there is to the p-series test.